Welcome to this presentation on pair sum in binary search trees (BST). Today we will explore a problem where we check for a pair of nodes whose sum equals a given target value in a BST. In this problem, we are given a binary search tree or BST and a target value. Our task is to determine if there exists a pair of nodes in the BST such that the sum of their values equals the target. Let's consider the first example. Here we have a BST with the values 7, 3, 8, 2, 4 and 9 and the target sum is 12. Upon checking, we find that the pair of nodes 8 and 4 adds up to 12, so the output is true. Now let's look at another example. In this case, the BST is 9, 5, 10, 2, 6 and 12 and the target sum is 23. However, in this tree, there's no pair of nodes whose values sum up to 23, so the output is false. To solve this, we will use a hash set. The approach involves performing an in-order traversal of the BST while keeping track of the visited node values. For each node, we check if the complement of its value, target minus node value, already exists in the set. If it does, we have found a pair. If not, we continue the traversal. Here's the code for the solution. The findPair function recursively traverses the BST, checking for pairs as it goes. It uses a hash set to store the node values in it has already visited. If it finds a complement in the set, it returns true. Otherwise, it continues checking the left and right subtrees. The key aspect of this code are if the node is null, we return false. The hash set is used to track the values of the nodes we have visited. If we find a value in a set that completes the sum, we return true. The time complexity is big of n because we visit each node once, and the space complexity is also big of n because of the hash set. Let's analyze the time and space complexity. Since we visit each node once in our traversal, the time complexity is big of n. The space complexity is big of n as well. Because the hash set stores up to n elements, where n is the number of nodes in the BST. In this problem, we have considered several edge cases. These include a single node BST, a tree where all elements are smaller than the target, cases with duplicate values, and large trees with up to 1 lakh nodes. To summarize, we use a hash set to track visited values. We implement a depth-first search to traverse the tree. The approach achieves big of n time complexity and big of n space complexity. This method provides an efficient way to find a pair of nodes in a BST that sums to a given target. Thank you for your attention. If you have any questions, feel free to ask.